Okay, welcome everyone, and thank you for the organizers first for putting this event together finally after 2 years of waiting for it, and also for Karol for inviting me to give this talk here. Maybe just two disclaimers before I start. I come from the quantum info side, so maybe it might be slightly different my approach to the sort of previous talks, but I hope to nevertheless give everyone something interesting to take home. And also, unfortunately, tomorrow in the afternoon I have to leave, but I'm very happy to take any questions on the boat or during lunch tomorrow or any time. So I will talk about something we call mutually unbiased measurements, which are not exactly the same as mutually unbiased bases, and also a characterization in terms of what we call Hadamard matrices of unitaries. And this is kind of a collection of results from 3 papers. And the first one is more like on the quantum info side. If you're interested in these Hadamard matrices, I recommend you the second paper. And the third one is kind of back again in the quantum info and Bell non-locality area with some kind of numerical approaches to try to say something about the MUB problem. So these are the papers that I will mention results from. So to start with, okay, this is something that luckily many of you have already talked about today. So I come from the sort of MUB side. So I'm mostly interested in MUBs. So 2 bases on finite dimensional Hilbert space with uniform overlaps, right? And then, as this was mentioned before, basically the only thing that matters, the thing that kind of characterizes these 2 bases are these phases. If I write one basis in the other, then only the phases matter. And if I collect the phases in a matrix, this will be a complex Hadamard matrix. So then we kind of establish that the complex Hadamard matrices basically define a pair of MUBs. But also from the quantum info side, the measurements that correspond to MUBs are widely useful. So this is how I kind of got into all of this MUB business. So for those of you that might not be like very familiar with quantum measurements, basically I'm just looking at the projections, right? The projections onto the basis elements, and a quantum measurement in general is just a collection of positive semi-definite operators that add up to the identity. So I'm interested in these MUB measurements because they are very useful in quantum info, and to me it seems that the property that makes them useful is complementarity. So now if I give you kind of an alternative definition of MUBs in terms of quantum measurements. So I say that 2 projective measurements on a d-dimensional Hilbert space are MUBs if they are complementary. What do I mean by that? Because also if you ask different people about complementarity, they might tell you something different. What I mean is that if there is a state, the normalized vector in the Hilbert space, that gives you probability 1 as an expectation value on one of the measurement operators from the first measurement, then the other measurement will give you a uniform outcome, and the other way around, right? So if I have a state, it gives me a definite outcome on one of the measurements, then the other measurement will always give me a completely uniform outcome. And this is what some people call complementarity, that these 2 measurements are complementary. So this is a completely valid definition of MUBs or Hadamard matrices, if you wish. Now, we took this definition and we were interested in what we call in quantum info a device-independent approach. The only thing I mean by this is that if you think of your measurements as some kind of actual measurement devices, and they are not sort of fully characterized, you don't know what is the dimension of the Hilbert space that they operate on, then, well, you shouldn't assume this in your definition either. So one way of thinking about what we call mutually unbiased measurements is you take the same kind of complementarity definition of MUBs, but you just take out the dimension of the Hilbert space. You just say, I have some Hilbert space. I will assume this to be finite dimensional, mostly just like kind of to be safe. And you have some Hilbert space, 2 projective measurements on it with D outcomes. So now when I say D, unlike Ingemar, I'm not always meaning the dimension. So be careful with that. But I have 2 D outcome measurements that have this same sort of complementarity relation. But now the dimension of the Hilbert space is not necessarily the same as the outcome.
why do we assume at all that they're projective?
It's a very good question, but this you can always kind of assume in like a Bell scenario. You can say, well, I can always take the dynamic dilation of whatever measurements I have. But it's true that this is sort of debatable how operational this is. But at least we took out the dimension, and these relations are really something you can observe in an experiment. Let's say these are probabilities pretty much. So we have this more or less operational definition, and we show an equivalent purely algebraic definition. So this first line is really just to say that these are measurements, and they satisfy these kind of algebraic relations. And well, it's kind of easy to see that MUBs will satisfy these. It's also clear from this definition, right? And well, the resulting measurements will have very similar properties to MUBs. I will not really go into the details of that. Maybe not everyone is interested in these. If you are interested, I just plug in some words like entropic uncertainties, measurement incompatibility, and many properties that are sort of interesting in quantum info. These MUMs have the same values, properties as MUBs. So, in a sense, they are very similar. But so how similar actually they are? And in order to study this, we try to kind of rewrite this characterization maybe in some other way. So the first thing we could show is that it's actually, I think this is already shown by Navasquez, Pironi, and Asin in some characterization of MUBs. But if you have these relations, these MUM relations, then your Hilbert space dimension must be a multiple of D, which is the outcome number now. So my Hilbert space looks like this. And well, then I can always find a basis such that the first measurement is projective. And okay, on the first Hilbert space, I have kind of a basis. And on the other one, it acts like the identity. And then I write the other measurement operators in a completely arbitrary form. This could be, if X is anything, then okay, this is a fully general form of these measurements. So what we can show is that these X operators must be the product of two unitaries, these UPGs. So actually, I don't need D squared operators to describe these measurements. I don't need D cube. I only need D squared. So they are unitaries, and they satisfy certain orthogonality relations. And okay, this might not look very nice, but since I already put here Hadamard matrices, maybe some of you already start to see that there's some connection to Hadamard matrices here. It will be maybe more apparent on the next slide. So it's a bunch of unitaries. They satisfy some sort of orthogonality-like relations, and I can kind of always choose the first ones, the lower index or the upper index, the first one to be just the identity. And if these both hold, then I call this the canonical form, which is basically just a choice of basis on this Hilbert space. So yes, a pair of these measurements is described by such unitaries. And it's again kind of easy to see that if I plug here this second auxiliary Hilbert spaces of dimension 1, then I get back the MUB definition. And these unitaries are pretty much just the phases that define the second basis. So to make the Hadamard property kind of clearer, I now collect these unitaries that describe my measurements in a block matrix with these unitary entries. And then there were these orthogonality relations that I had before. This is basically saying that this matrix is a Hadamard matrix, but now the entries, so they are not like entry-wise unit elements; they are unitaries, right? So if these are of dimension 1, then they are unit complex numbers. But more generally, they could be unitary matrices of some arbitrary dimension.
One condition implies, of course, the other.
Yes.
What about the higher dimensional case?
Sorry, which higher dimensional case?
So when these are really unitaries and not just complex numbers, it's still true that one condition implies the other.
You mean these two?
Yes.
If you just think about the unitaries, I'm not sure. But once if you know that these come from measurements, then yes, these are redundant. If you start kind of from the measurement side, you build these kind of Q operators, then actually you kind of don't need this second one. But I just kept it there for completeness. If you kind of forget about the measurements, I'm not exactly sure anymore. Right, and again, if you plug in, okay, each of these blocks are of size of dimension 1, then you recover a complex Hadamard matrix. And then this canonical form that I had, which is saying that the first column and the first row is just identities, this would be a dephased complex Hadamard matrix. And I just put up an example here so that you see that these kind of exist in some non-trivial way. These are all the Pauli XYZ operators. So this is an example of a Hadamard matrix of unitaries.
So practically, 1 means here identity of size 2.
Yes.
So this matrix is of size now 2 times 6 or 12. Yes.
Yes. Correct. Yes. Right. So this is maybe the nicest looking example that we have for now. And right. So we keep with this characterization, we start asking questions. Well, how similar actually these measurements are to MUBs? And the first thing one can think of is, well, the Hilbert space I mentioned is a multiple of D. Now I can take on every subspace of dimension D, I can take some MUBs, and these will also satisfy these MUM conditions, right? If I say if my Hilbert space kind of factors to some D-dimensional ones, and on each of these D-dimensional Hilbert spaces, my measurements are just MUBs, then I call this a direct sum of MUBs, right? Okay, these will also be MUMs. And then we have a nice characterization of when MUMs are direct sums of MUBs. And this is if and only if these unitaries in this Hadamard matrix of unitaries, all of them pairwise commute in the canonical form. So you find the basis in which the Hadamard matrix is canonical. You look at all the unitaries. If they all commute, then you can write it as a direct sum of MUBs. If there's a non-commuting pair, you cannot. And okay, in the previous example, you already saw that sometimes there exist these canonical forms of Hadamard matrices with non-commuting entries. We had like Pauli X and Z operators. So in this sense, okay, they are very similar to MUBs, but actually strictly more general, right? Like I can write some kind of high dimensional MUMs that will not just be like, taking copies of perhaps different MUBs. It's really sort of like entangled in this larger space. So this is one way in which they are different. And then, well, this previous example I showed you, we found it kind of in an ad hoc way, let's say. But then we were also looking at like how to try to construct them in a systematic way. And one nice connection that we found is a connection to quaternionic Hadamard matrices. So here I just kind of remind you of the algebra of quaternions. Now you can take a matrix with quaternion elements, and again, I can define a Hadamard matrix, right? I can say that, well, if they are all unit quaternions and they satisfy this same kind of Hadamard relation, I have a Hadamard matrix of quaternions. Now, the reason why these can be used for constructing interesting MUMs is because now two quaternions do not necessarily commute. And so, maybe there's some kind of relation. And in fact, you can define a map from quaternions to linear operators of a two-dimensional Hilbert space. Okay, you take the linear extension of this map, and okay, what you can show that it has sort of all the right properties. It defines an isometry on like the right subalgebras, and what you can actually show is that if I have a Hadamard matrix, a quaternionic Hadamard matrix M, now I define this Hadamard matrix of unitaries. Well, if I define it in this way, this will actually be a Hadamard matrix of unitaries. So whenever I have a quaternionic Hadamard matrix, I can map it to a Hadamard matrix of unitaries of size 2, right? With the Pauli matrices. So then we can look at what people know about quaternionic Hadamard matrices, and so whenever we find one such that in the dephased form of the quaternionic Hadamard matrix, we have that all of the elements commute, then we have direct sums of MUBs in the corresponding MUMs. And the other way around, if we find some quaternionic Hadamard matrix with some non-commuting entries, then we actually found MUMs which are not direct sums of MUBs, right? And there exist some constructions In particular, we found some in the thesis of Kuznetsov, who found quaternionic Hadamard matrices. The construction is based on these perfect sequences. I think maybe Marcus mentioned perfect sequences. There are perfect sequences of quaternions from which you can construct some kind of circulant quaternionic Hadamard matrices. And there are many constructions here for some small prime dimensions up to like 20 something. I just showed you like one smaller example in dimension 5. These are just the quaternion units, right? J is one of the units, and Q is this kind of equal combination of the units. And it's clear that, for example, J and Q in conjugate do not commute. So if I map this now to a Hadamard matrix of unitaries, I get MUMs, which are not direct sums of MUBs. And we can construct many other such examples from these small prime dimensions.
Is it the smallest non-trivial example?
The smallest non-trivial example is dimension 4. It's actually a good question. So if you have outcome number 2 and 3, then in fact every MUM is a direct sum of MUBs, because you can kind of see that you don't really have that much freedom in what unitaries you can choose. And the freedom you're left with, you can only choose commuting ones. So
number 4 is the simplest non-trivial.
Yes. And actually for number 4, there's also, I didn't put this here, but there's another construction of a one parameter family of quaternionic Hadamard matrices. And okay, this maybe it's not even one parameter. There is some infinite family of quaternionic Hadamard matrices, and this also gives us an infinite family of MUMs, which are not direct sums of MUBs. Yeah, so these are the smallest examples. So you can see, yeah, we saw these kind of difficult differences that they are not always direct sums of MUBs, which might be kind of the simplest thing you can think of. Then another question is that everybody always asks, from me at least, is like, okay, you have these kind of generalizations of MUBs, how many of them you can find? And we all know that in dimension D, you can find at most D plus 1 MUBs. Now, there's a big difference, because for a given outcome number D, there are unboundedly many of these MUMs, because basically you can start increasing the dimension. And I even give you the construction. You can construct these operators. I construct n operators, and I take the projections. These will all have sort of degenerate eigenspaces. These are the generalized X and Z operators. I can take the projections onto the eigenspaces of these guys. And okay, you can show that basically any pair of these two will commute like Pauli X and Z. And then from this, you can basically deduce that there's a unitary, for every pair, there's a unitary such that the operators look like Z and X tensor identity after this unitary. So from this, you can also see that these are MUMs, right? These are just direct sums of MUBs if you take this just a pair. So every pair is an MUM, and I can construct as much as I want if I kind of increase the dimension, increase the number of tensor factors. So I can really find as many as I want. So if I kind of want to try to relate this to the MUB problem, then I need to do something more. And this something more is what we are trying to do recently. So okay, on these last few slides, I apologize from the non-quantum info people, but I will not have time to like explain Bell inequalities. But this is pretty much like this bipartite scenario. There are like measurements, analysis on both sides, and there's a tensor product Hilbert space which shares a quantum state. And a Bell functional is basically just the trace of the state with the product of these operators. And okay, these are kind of the probabilities that you have, and you have a linear functional of these. Now you can, this is a real number. You can try to optimize it over all states and measurements. So this is a Bell functional. We introduce Bell functionals for any D such that the maximal value you can get for any quantum state and measurements is this square root of d minus 1. And this maximal value, it actually certifies that the measurements that I can use here, they must be MUMs. And in fact, any pair of MUMs will give you, with a suitable state, will give you this maximal value. Now, this is kind of nice, but maybe how can I use this to now try to tackle the MUB problem? Well, what we do, we can extend this Bell scenario to, you see here I have the choice of just 2 measurements for Bob. I can extend it to n measurements. We have a kind of a fairly trivial extension of this Bell functional to n measurements. And then again, this will have a maximum value, which you can only attain with n mutually unbiased measurements. And in fact, any set of n will do. Okay, so far so good, but these always exist, so this is not very useful. But now if I, in this Bell scenario, if I restrict the dimension to be the same as this d here, then in fact the maximal value of this Bell functional in this fixed dimension certifies exactly MUBs. So if I can find the maximum value of this Bell functional in a fixed dimension, I can actually sort of answer the MUB existence problem for any d and n. Okay, so this is not an easy task again, as you might guess or know. So the first thing that we did was pretty much just heuristic optimization methods, various methods of trying to find states and a state and measurements that would maximize the Bell functional. So in this table, we have basically this normalized Bell functional value. So this is 0 if you find the optimal value and something larger than 0 if you didn't. And then, okay, in this table, we see that basically okay, the known cases are sort of recovered properly, correctly, right? We always find the maximal value when n MUBs exist in dimension d. And then also here these are also known cases, right? So when they don't exist, we do not find them, luckily, right? And then we applied also the methods for dimension 6 for MUBs. We didn't find 4 MUBs, but again, these are sort of heuristic optimization techniques. So the